in this lecture we are going to start with our discussion that what we were doing, and the discussion we were doing was on the method of images. Okay, so today we are going to continue with that discussion only. Um, okay, but today we are going to move on to a very special case, that is method of images, and especially we are going to discuss uh, one important case, which is the case of the grounded conducting sphere. Case of the grounded conducting sphere. This is what we are going to do today. Okay. Uh, okay. So till now we have done cases where we had a plane conducting sheet. Today we are going to do a case where we will have a grounded conducting sphere. This is an important topic, and then we'll do, as we complete this topic, then we are left with only one thing, that is doing problems. Okay. So we'll take a marathon sort of session, a big session where we are going to complete all sort of different problems that have been asked in the examination, and also otherwise which are important for examination. Okay. So this serves as your last class in the theory section for the method of images. Okay. So what is the problem exactly? So problem is that let us say there is a conducting sphere. Okay, so there is a conducting sphere which is maintained at potential 0. So this is a conducting sphere which is maintained at potential 0. Okay, and the radius of this sphere is capital R. Okay, radius of this conducting sphere is capital R, and a point charge is kept at a distance 0, 0, z. The point charge is kept at a distance 0, 0, z. We want to find first potential, the potential at any point, let's say as a function of r and theta, that is okay. We also want to find what will be the induced surface charge distribution. We also want to find what would be the total charge induced on the surface due to this particular point charge. And we also want to find what will be the total induced charge. Okay, so all these queries you want to do, and all these things we have done for the cases of infinite. Also we can find what will be the force on this. Also we can find what is the force exerted on this charge q. So it's quite obvious that if this charge q is placed here, so there would be some negative charges which would be induced closer to it. Okay, and the positive charges will drive to the farther end. Okay, so there would be some non-uniform sort of distribution. So there would be some non-uniform charge distribution as a result of this particular charge q. Okay, so non-uniform, I should write induced charge distribution. So there would be some charges that would be induced, and this non-uniform charge distribution we want to find. That is one of our aims in this particular problem. We also want to find what will be the total induced charge over this particular surface, that is this conducting surface. Because of this charge, see, if this charge q is placed, so there would be some negative charge also induced. Because of this, it will feel a force. We also want to find what is the force exerted on charge q. So keeping all these things in mind, let us try to first develop an equivalent problem. That is, we did initially also. We wanted to develop an equivalent method of image problem. what we'll do, we'll try to establish an equivalent method of image problem. And what it is like, so what I'll do, uh, okay, what I'll do, instead of this problem, I will replace this problem by using method of images. So in method of images, we used to have a image charge, right? So here also we are going to put an image charge. We are going to put image charge. Let's see how. Okay. So let us say this is my here it was my charge place 0 comma 0 comma z. Okay, now I'll place an image charge here, let's say q dash, and I'll verify that whether placing the charge here would satisfy the boundary conditions or not. So right now, just satisfy yourself by saying that there is an image charge. So I'll place an image charge q dash at 0 comma 0 comma z dash. Okay, see, I'll choose see. This was grounded, so your potential will be 0, and this is an equipotential surface, so your potential would be maintained 0 throughout on the surface of the conductor. So let us say this is your point P, let's say this is your point Q. Okay, now instead of having this grounded, what I've done, I've simply placed an image charge here Q dash at place 0 comma 0 comma z dash, and here you have this point Q and this point P. So what I can do, I know that my potential at P will be equal to potential at Q, and these all things would be equal to 0, isn't it? So what will be potential at P? Achha, also one should remember this is r. Okay, so the radius is given as r. So this distance from here to here is z dash. So this distance from here to here would be r minus z dash, and this distance from here to here, that is from let's say from here to, like, from this place to this place, because this is 0 comma 0 comma z from here to here. So this will be, I think this will be the z minus of r, because 0 comma 0 comma z is referred from the origin. Okay, so this is one thing. Now you see, okay, now what will be potential at P? It will be 0, and it will be, should I write it as k q upon, sorry, z minus r plus k q dash divided by r minus z dash. This is 1, and this should be equal to 0. And what would be potential at q? So potential at q would be k, I think q divided by this would be, I think, z plus r, and then k q dash divided by z dash plus r. So from here to here, this is z dash, and this is r. So overall this would be the case, it would be 0. So let us say this is 1. So what I'll get that my q dash can be written as minus of q divided by z minus r, and this r minus z dash. And from here, if I want to find q dash is equals to minus of q divided by z plus r. So this is q, don't forget. Okay, and then there would be some z dash plus r. Okay, so both of these equations are equivalent. That is, if I want to say that my potential at so this equation is 1 and this equation is 2, and they're after all rendering you the same result. So let us equate them up. So let us equate. If I equate these two things, then what I'll get, if I equate these two things, I'll get that I will simply get, should I write? Okay, so I will get that r minus z dash into z plus r is equal to z minus r into z dash plus r. And here, if I try to find the answer, this will be zr plus r square minus zz dash minus rz dash, and this is zz dash plus zr minus z dash r plus r square. So r square gets cancelled, I guess, if I'm not wrong. Okay, and then there is some mistake somewhere. I don't know what is the mistake. I think z dash should be, this is r minus z dash, right? This is r minus z dash, this is z minus r, this is z dash plus r, this is, okay, this was minus r square, my mistake. So this was minus r square, okay. So this was minus r square, and z into z dash, z into r, minus z dash into r, and then minus r square. Okay, sorry, it will not get cancelled. Rather, minus z dash r gets cancelled, z dash remains, and zr gets cancelled. So you have overall, I can write 2 times z dash is equal to 2 times r square, and from here I will get z dash, which is equivalent to writing z r square by z. So this gives you the location of the image charge. Location of the image charge. So from here I'll get the location of the image charge. So if there's a problem where your charge q is placed in front of the, if you have a charge q placed in front of an infinite, sorry, not infinite, sorry, in front of grounded conducting sphere, you can reduce this particular problem, that is this particular problem, by replacing it with an equivalent image problem where the image charge is placed at a distance 0, 0, z dash, and this z dash is equal to r square upon z. This z dash is equal to r square upon z. Okay. Now one wants to find what would be the I should write what would be the value of the image charge, or what would be the magnitude, or what would be the charge, that is what would be the image charge. We want to find what would be the image charge. Okay, so I know that my q dash I have found from two different equivalent statement. Any one of them you can take. Let's say I'll take this one. So if that is the case, so minus q dash is equal to minus of q divided by z plus, if I'm not wrong, this is z plus r, and then multiplied by z dash plus r. Is that clear? And if I want to use this z dash here, what I'll get? I'll get minus q upon r plus z, and then I will get r square plus rz divided by z. So overall you will get that my q dash would be equivalent to minus of q r divided by z. So what you can find, one thing is very much clear, that this image charge is negative. That is fine. One has to see also that it depends upon the distance of the original charge from the center. So this particular image charge depends upon the distance of the original charge from the center, and rather it depends inversely to the distance of the original charge from the center of the sphere. So this is how it is. So at times these things can be asked in your examination in form of statement. So I'm just reiterating that. Okay. Now you must be thinking that is it right? Is it right as in matlab, I have only taken 2 points, and then I have given you this bold statement. So what I'll do, I'll try to verify this for you. So let us verify. Let us verify the above claim. And what is that claim? That our problem of a grounded conducting sphere with the charge q placed can be replaced by an equivalent method of image problem. Can be replaced by equivalent method of image problem with the image charge equivalent to minus of q r upon z placed at a distance 0, 0 r square upon z. So let us verify whether this is true or not. So see, one thing is very much clear that because this particular thing was very much clear that this was grounded. So in any case, I can say that my potential over this conducting sphere would be 0. Since it is conductor, it will remain 0 on each of these points. So therefore, this particular problem contains an azimuthal symmetry. This particular problem contains an azimuthal symmetry, that is, from whichever angle, whichever phi angle you want to see this problem, the potential will appear 0 to you only. As in, if you go there from here if you see the problem, from here if you see the problem, from here if you see the problem, from here. That is, if you see the problem from any of these 5 orientations, the potential would appear to you as 0 only. Okay, so this particular problem will have an azimuthal symmetry. That is, you will not have any phi dependence. And what I want to do, I want to find at any general point, let's say P dash, at any general point P dash, I want to find what would be the, potential given the point, charge and the image charge. So I'll reiterate my statement. Just give me a minute. So what I want to say, see, initially this particular conducting sphere was grounded. So what I did, I replaced this particular grounded conducting sphere with the help of a point charge and image charge. So here I had placed an image charge and here I had a point charge. So if I replace this problem, I am very sure that on the surface of the conductor, my potential should be 0. So if I replace this particular problem, that is the problem of a grounded conducting plane, the problem of a charge placed in front of a grounded conducting sphere by an equivalent method of image problem, that is where I'm placing Q and Q dash, my potential must be 0. That is, it should keep my boundary condition intact, isn't it? So what I'll do, I will verify this for you. So I'll place Q dash here, and there is a Q here, and this Q is placed at 0, 0, Z, and this Q dash is placed at 0, 0, R square upon Z. And you know what is your Q? Q is minus QR upon Z. And I've already told you that this particular problem is having azimuthal symmetry. So what I'll do, I'll try to find what is the potential as a function of r comma theta, because there is no such phi dependence, because from whichever phi angle you want to see the potential, you will find that potential is 0 only. So it is symmetric with respect to phi angle. So there is only dependence on r and theta. There is only dependence on r and theta, and I want to find potential at any general point r comma theta. That is what I have written as P dash here. And let's say this particular P dash from here to here, this will be at a distance r. So I don't think there is an issue here. This r is the radius of the sphere. Let's say this distance I'm going to say, let's say d dash, and this distance let us take it as d, and let us take this angle as theta. So what do you think the potential on P dash would be? So potential on P dash would be equivalent to writing minus k q r by z root over what would be d dash. So d dash would be r square, and this is a square, like this distance square. This distance is r square upon z. So I'll write r square plus r ki power 4 upon z square and minus 2r square. Not r square, I think r cube will be there, z, and then I will have cos theta plus what would be this distance would be kq upon d, and what is d? D would be root over, this is entire distance is z, and here it is r, so I'll write r square plus z square minus 2zr cos theta. Okay, so potential at P dash would be equal to, if I want to use this r here, so I'll put this r, I'll bring this r in the denominator side, and when I'll do so, I'll get minus kq root over this r square would get cancelled, inside I'll get a z square, then plus I'll get an r square, and then minus 2r z cos theta, and this will remain as it is. So I'll write kq upon root over r square plus z square minus 2zr cos theta. Clearly this is 0. So at any arbitrary point on the conducting sphere, due to the placement of this charge q dash and this q, the potential at any arbitrary point, so this P dash was any arbitrary point, right? So this at any arbitrary point you will get potential as 0. So if you replace this entire problem, the initial problem was that there was a grounded conducting plane and a charge q was placed in front of it. So if you replace this original problem by an equivalent problem of having an image, of image method of image problem. That is, if I place a q dash here and q here, and then I want to find if I want to find the potential anywhere on the uh, sphere of the conducting sphere, I'll get it 0 only. So by this q dash, by placing this q dash at 0 comma 0 comma r square by z, where q dash is given by minus q upon z, the the boundary conditions are met, the boundary conditions are satisfied. So this indeed is the correct thing. So I'll replace my original problem by uh, so I'll write here my original problem can be replaced by an equivalent method of image problem from the center of the sphere. Okay, so I think this is quite clear. Now next one wants to find, next what I can find is what do you think would be the potential at any general point? So potential r comma theta would be, I can write it as v as function of r and theta. It will be equals to what? It will be equals to kq divided by root over r square plus z square minus 2zr cos theta minus kqr by z divided by root over r square plus r की power 4 upon z square minus 2r square z cos theta. Okay. Okay, so this will be a potential in general. So if I want to write it in better way, uh, this would be it. Okay, so this will be potential at any general point. So this, let's say this is my conducting sphere. At any general point as a function of r and theta, if I want to find my potential, then this will be the expression of the potential. This will be the expression of the potential, because see, now it is at a distance small r, okay, and this q dash is at distance 0 comma 0 comma z dash, where z dash is r square upon z, and this is q is at 0 comma 0 comma z. So if you want to use now law of cosines, you can use, this is theta. So this distance now would be given by root over small r square plus r square upon z ka whole square minus 2r r square z cos theta, and this distance can be written as, so you have to use the law of cosines and then you can clearly write it. Why I'm interested in potential as a function of r and theta? See, I have already told you that whenever I want to find my induced surface charge density, whenever I want to find my induced surface charge density, what I do, what I have done previously also, I am interested in finding the normal derivative of the potential. So normal to this surface is the radial component. Normal to this surface of the sphere is the radial component. So what I would be interested in, I would be interested in finding the radial component, or radial component of the electric field or the normal component of the electric field, which is radial component, by using this minus del V upon del R at R equals to capital R. So I know that near the surface of the conductor, the normal the near the surface of the conductor, the normal component of electric field is given by sigma upon epsilon naught. So if I find the sigma upon epsilon naught, that is an if I somehow find the normal component of the electric field on the surface of the sphere, I will be able to extract my induced surface charge density from here. So this I can equate to sigma upon epsilon. Okay, and so if I do this, so what I'll get? So I'll get simply first let us differentiate this one. Sigma upon epsilon naught is equal to, let us differentiate this one. So this will be K Q, and with respect to R, if I want to differentiate it, sorry, with respect to R, if I want to differentiate it, then what I'll get? I'll get simply 2R minus 2Z cos theta, and this particular thing will become, I think, R square plus Z square minus 2ZR cos theta raised to power 3 by 2. There would be a minus half also, so this will get cancelled. There would be a minus half also. Okay, so there would be a minus half also. So I'll write, I'm first finding what would be del V upon del sum. So there would be a negative. There would be a negative because of the derivative part. Minus half would come in front, and then there is again a negative here. So I'm not writing anything. I'm just writing this thing. Then plus, sorry. Then again the derivative with respect to this will be, I think, minus KQ. So negative is there. Don't forget the negative part. Otherwise we'll get confused. And once we are confused, then things will not come to our favor. So minus KQR upon Z. What I will get from there? So from here I will get negative sign minus half in front, and from here I'll write it is equivalent to writing minus, this is Z, okay, don't forget this is Z. So this is minus R, sorry, this is minus R square upon Z cos theta plus R divided by divided by root over, sorry, not root over, R square plus R की power 4 upon Z square minus 2R R square Z cos theta, and this whole raised to power 3 by 2. This whole raised to power 3 by 2. Okay, now if I want to if I want to differentiate, एक बार इसको ढंग से differentiate कर लेते हैं, because I think there is some mistake here. So let us differentiate it properly. So I'm differentiating it here. So wherever I'm making the star, let us differentiate it there. So this was what I wanted to differentiate. So we want to find del by del R of minus of KQ R upon Z, this whole divided by this whole divided by root over small r square, then plus r की power 4 upon z square minus 2r r square upon z cos of theta. So I want to differentiate. Let's see what I'll get, and let us forget once for all this entire bracket, so that I'll write it all over again, don't worry. Okay, so that there is no mistake as such, because once we do a mistake, then things will not come to our favor. Okay, let us first take the derivative part of this. Okay, Let us first take the derivative of this. Okay, so what I'll get, एक काम करते हैं, let us easy it. So what I'll do, I'll take this KQ, that is absolutely fine, and I will place this R upon Z below so that things become easy for me. So I'll get it as R Z upon capital R whole square plus I think R square, and then minus 2, I think this is Z, there would be R, and there would be cos theta. So minus 2 is RZ cos theta plus R square, and then I will get RZ whole square. I hope it is quite clear now. Okay, so I want to differentiate this term. This is the second term here. This is the term that I'm differentiating, and this term I will also let you know how did I differentiate it. So del by del R, I'm not writing negative here, I'm just trying to differentiate it. So this would be equal to minus of KQ, and if I differentiate it, what I'll get, I will simply get minus of, I'll write it once here, minus of 1 upon 2, 1 upon this entire thing raised to power 3 by 2, and then I have to differentiate this entire thing all over again. Okay, so I have to differentiate this entire thing all over again with respect to R. Okay, so what I have done, I have differentiated it, so this derivative will come as minus 1 by 2, and this will, and I have to differentiate this entire term with respect to small r. So with respect to small r, I'll get 2r z upon r square minus 2z cos theta. Okay, and effectively I will get this as, this minus minus gets cancelled, so I'll get k q, and this r square still remains, I guess. This r square still remains. I don't know why, but this remains here, so I'll write this minus minus is there. Okay, so this minus minus remains there, so I'll get, I have this r square, rz square upon capital R square, and then I have this, I've gotten rid of this 2, this minus of z cos theta divided by rz upon capital R whole square, then plus r square minus 2 z small r cos theta whole raised to power 3 by 2. Okay, so this is my second second term. Okay, my first term is quite easy to see, so I'll just replace it. So what will be the derivative of this part? So derivative of this part, I'm just doing del v upon del r. So what I'll do, I'll write here minus sigma 1. So what will be del v upon del r? So it's quite clear that the first term here, the del upon del r of kq upon this entire thing, r square plus z square minus 2z capital R. I think this is not capital R, I think this should be small r. Just verify it once, this should be small r. So this is small r here, and then cos theta raised to power 1 by 2. So what I'll get, I will get simply minus 1 upon 2, this is kq, and then I will get r square plus z square minus 2z r cos theta raised to power minus 3 by 2, and then I will get 2r minus 2z cos theta. So if eventually I will get this as this particular thing as, I think this I will get minus of r plus z cos theta divided by, and this kq would obviously accompany, so I'll write kq here, plus r square plus z square minus 2zr cos theta whole raised to power 3 by 2. I'll use this term and I'll use the other term, and I will find the total normal component of the electric field. So the normal component of electric field, I'll write it here. So the normal component of the electric field, that is the radial at r equals to r we want to find, is equivalent to writing kq, the first term was minus r z cos theta divided by r square plus z square plus, sorry, minus 2rz cos theta whole raised to power 3 by 2, and then this term. So this term would be plus I think r z square upon r square minus z cos theta divided by, because this by plus because I've already taken negative derivative, so don't worry about it. So rz up a whole square plus r square minus 2zr cos theta raised to power 3 by 2. And this all thing we have to verify at r equals to capital R. Okay, so this will give you the normal component of the electric field, that is the radial component of the electric field at r equals to capital R, and this I'm leaving to you as a homework. This you will get as this normal component of electric field at r equals to capital R, that is the radial component of the electric field. You will get it as k q upon r, then you will get z square minus r square. This is quite a tricky and long derivation, but somehow I wanted to do it so that in examination, if you get somewhere out of like, if you just cannot do all these things, if you do not remember the result, then at least you can do all these things. Okay, so this is the radial component of the electric field, or that is the normal component of the electric field, and what it is equivalent to, it is equal to sigma upon epsilon naught. So your sigma would be minus 1 upon 4 pi, and there is a q here, there is a r here, and then z square minus r square divided by r square plus z square minus 2zr cos theta whole raised to power 3 by 2. Okay, so this will be your sigma. Sigma is the induced surface charge density, and clearly it depends upon the distance of the charge from the center, original charge from the center, also depends upon theta. So this is quite non-uniform sort of distribution that we also expected, because closer to the charge, closer to the original charge, more induced charges will appear. Closer to the charge, closer to the original charge, that is not non-image charge I'm talking, more induced charges we are going to obtain. So it is more likely that on this side of the hemisphere you are going to have more negative charge, and this side of the hemisphere will have more positive charge, but the density here would be more. Okay, so somehow we understand that obviously this would be some non-uniform charge induced surface charge distribution only, which is quite clear from our calculation also. What would be the force exerted on charge q? Clearly force exerted on charge q would be k q q dash divided by, what is the distance between them? The distance between them is z minus r square upon z whole square. And what is q dash? You know that q dash is also equivalent to, what is q dash? Q dash is simply equal to minus of q r upon z. So instead of writing minus q, I'll simply write that the force vector would be in the negative z direction. So it will be equals to k q square r upon z, and then I will get z square minus r square whole square divided by z square. So this z you will get cancelled. So here I will get this, and this will be in the negative z direction. Okay, so because there is a point charge which is negative, sorry, image charge which is negative, the original charge was positive. So obviously this is going to attract it in this direction. So towards minus z cap, this would be the expression of force, that is k q square z r upon z square minus r square whole square. This is the force that your original charge will feel. Okay. Now, if I want to find what would be the induced charge, what would be the total induced charge? So if I want to find what is the total induced charge, then what I have to do, I have to simply integrate it. So over the surface. So this is my sphere. This is my sphere, and I will take a patch over it. So I'll simply take a patch over it. R square sine theta d theta d phi r cap. So this will be the patch ds, and simply sigma into ds will give me total charge induced. Integrate it and you will get the result. So if I integrate it from 0 to 2 pi, that is d phi would be integrated from 0 to pi, d theta would be integrated from 0 to pi. So what I will get, I will simply get, I think this is minus 1 upon 4 pi somewhere. This is minus 1 upon 4 pi. So what I'll do it, I'll write it as it is. So I'll write it as it is. Just give me a minute. Okay. So I'll write this particular expression here. So what was my sigma? My sigma was, I'll write it somewhere here so that my sigma is equal to what? My sigma is equal to minus 1 upon 4 pi q upon capital R, and then this is z square minus r square divided by r square plus z square minus 2rz cos theta whole raised to power 3 pi. Okay, so this is my sigma, and I want to use this sigma in order to obtain the total induced charge on the surface of the this conducting sphere. Okay, so that will be equal to sigma into ds, and that sigma into ds, because ds would, like, I'll write this will be equals to 2 pi integration sigma d theta from 0 to pi, because there is no such term of phi here. So obviously this 2 pi would integrate, d phi would integrate from 0 to 2 pi. This is what I'll get, and if I integrate this thing up, I'll get 2 pi. So this will be minus q upon 2, and there is a r here and there is r square here, so I'll write r outside. Okay, I'll write r outside. This z square minus r square will also come outside. And now I have to integrate from 0 to pi. The sine theta would survive, so sine theta d theta divided by r square z square minus 2rz cos theta whole raised to power 3 pi. So how to integrate it? I will take this as some t square or something. So this minus 2rz, if I multiply and if I divide, so I'll multiply minus, I'll simply multiply 2rz here, and I will divide 2rz here. Okay, and if I do so, what result I will get, I'm going to straightway write it. Not chalo straightway nahi likhte isko. So this is t square, so this will become 1 upon t cube, and this will become 2t dt. See, if I differentiate this term inside, if I differentiate this, r square would go to 0, z square would go to 0 with respect to theta. If I differentiate, this will become minus 2rz cos theta derivative is minus sin theta. So 2rz sin theta d theta will become 2t dt. This is what I'm doing. And this integration would eventually become 2 upon t square integration, and this is dt, like 2 upon t square. And I will simply get minus 2 upon t. Okay, so this is what I'm going to get. So this is what I'm going to put. Okay, so I'm going to put this only. Okay, this negative I think would get cancelled. This negative would get cancelled. So I will get q capital R z square minus r square divided by 2 times capital RZ, and this 1 upon, what is t? T square is this, so 1 upon root over r square plus z square minus 2rz cos theta, from where to where? From theta equal to 0 to theta equals to pi. I think r would get cancelled here also, so I'll not write even r, so that I have cancelled. Okay, so effectively, now you see, I've already told you in the initial lectures that whenever you have to find modulus root over x square, it is equals to modulus of x. Don't forget, because this is going to create certain troubles. So this, from here I know my total charge induced would be equals to q upon 2 z square minus r square, and if I replace theta equal to pi, I will get 1 upon r plus z ka mod minus theta equal to 0, I'll get 1 upon mod of r minus z. Okay, so this is r minus z ka square, or z minus r ka square, I'll get 1. Now in the condition that if if z is very far away from r, that is z is greater than r, then the modulus will so operate that I will get this. So if that is the case, I will get this. So I will get z plus r, and fine here. Here I'll get, because z is way too greater than r, so I'll write z minus r. From here, what I'll get, I will simply get q upon 2z. I think z was there, I forgot somewhere. Z, and then I have this z minus r minus z minus r divided by z square minus r square, and then again I have this z square minus r square. So this gets cancelled, z gets cancelled, so you will get a total induced charge on the conducting sphere as minus of q capital R divided by simply z, because this 2 would get cancelled eventually. So this is the total induced charge that you will have on the surface of the conducting sphere, because of the presence of charge small q at 0, 0, z from the origin. So I hope this is quite lengthy. Mostly, none of these things are going to be asked in examination. If my suggestion would be to at least you should remember these results. Not these. These are very lengthy results. At least remember. At least remember what is the image charge. So image charge is equals to minus of QR upon Z. And another thing that you should remember, that what would be the distance, that is R square. So for your net exam, mostly the things will be done if you know these two things. Okay, but otherwise we'll see much of these problems. So now only the method of images lecture, only one class is left. So we'll take a long class and we'll try to finish all the PYQs. Also, we are going to do some random questions as well for revision. Okay, so I think to meet you I wish to meet you tomorrow, and till then, keep a great care of yourself.